Hello and welcome to this project update video. This video is going to outline the progress and current results of my final year project. The project's goal was to determine whether a net drag reduction could be produced when introducing a breakup device into turbulent flow. The device introduced breaks up large eddies and present above a rough wall to produce drag reduction. This was tested using computational fluid dynamics, or CFD. In this video, I'm going to give some background information on the large eddy breakup phenomenon and computational fluid dynamics. I will then cover how the model was validated against previously completed research and talk about current results and how goals have changed over the course of the project. So firstly, I want to quickly go over what large eddy breakup, or LEBU, actually is. It is a relatively niche subject that many people may not have knowledge of. In a turbulent regime, large eddies are vortices where fluid tends to swirl behind an object that interrupts flow. In these eddies, the fluid can be reversed and flow upstream, creating a vortex. These large eddies account for large amounts of turbulent energy present in flow. Large eddy breakup aims to interrupt these vortices by placing a device within the boundary layer of a wall, effectively reducing the drag on the wall. For example, this LEBU device has been placed within the turbulent boundary layer of a smooth wall. The turbulent energy is relatively uniform before the LEBU is placed. However, after the LEBU, there is a noticeable reduction in the turbulent energy, before eventually returning to the uniform energy shown before. This is reflected in the drag on the plate. LEBU devices have proven to reduce drag against a smooth wall. However, the drag introduced by the device tends to be greater than that of the reduction. A net drag reduction, where drag introduced is less than drag reduction, has not been reliably produced to date. The original goal of this project was to test a LEBU against a rough wall to see if a net drag reduction could be produced. A deep understanding of CFD is not necessary to understand this project, but I will just briefly cover some of the concepts to explain some of the decisions I made whilst building the model. There are three main types of CFD: Reynolds average Navier-Stokes, large eddy simulation, and direct numerical simulation. RANS, LES, and DNS, respectively. RANS models are the least accurate, only solving on a large scale and modeling everything else, whilst DNS solves everything. LES solves more than RANS, but still models the smaller scales. While using RANS, there are various models available to use, each with their benefits and drawbacks. There are also different solvers available. I'll primarily be talking about Fluent and CFX, as these are the two available in the ANSYS software package. Fluent is generally preferred for looking at external flow over objects, like in a wind tunnel, while CFX is more useful when looking at pipe flow and turbomachinery. Fluent was chosen for this project because it consists of external flow over plates and geometries. For these solvers to work, however, the user must input what is called a mesh. Mesh is a group of control volumes, which gives the solver locations at which to either solve or model the governing equations. ANSYS has several software options available, which let the user turn geometry into a mesh, including ANSYS Meshing, ICEM Mesher, and Fluent's built-in Mesher. ANSYS Meshing is mostly automated, allowing the user minimal control over the mesh parameters but taking little time, whilst ICEM Mesher requires the user to create the mesh, allowing more control but taking significantly more time. The first part of the project was to create a model that could accurately capture both a rough wall and a LEBU device. In order to achieve this goal, the model would be tested with both these geometries separately. Validation data could be found for both rough wall studies and LEBU device studies. Two-dimensional geometry was used, both to decrease solve time and decrease meshing complexity. This was to eventually move to 3 dimensions, but due to computational limitations, the project has remained in 2 dimensions. So the first stage of the model consisted of only a smooth plate, shown here. This was to ensure that the RANS model used was generating realistic results, and that Y+ values along the wall were within acceptable ranges. Y+ basically represents a local Reynolds number, and the mesh's first cell height was tailored so that Y+ was below 1. ANSYS native meshing software was used in this case, as it automatically created high-quality meshes for such a simple geometry, and the only parameters controlled are an inflation layer coming off this bottom edge, and forcing the mesh to be quad-dominant rather than tetradominant. This would speed up solution time significantly. In terms of the solver, the settings were left at Fluent's recommended, and the shear stress transport K omega model was used for its versatility and relatively fast solve times. Boundary conditions were set simply. There was a 20 meter per second inlet velocity imposed on this front edge, and this rear edge was an outlet with no conditions. Top edge was free, so no shear whatsoever, and then bottom edge had a no slip condition. For validation, the velocity profile at momentum thickness Reynolds number 1000 was compared with a reliable DNS study. The velocity profiles at different points down the plate were also compared. The second stage of validation was to test if these settings could correctly capture the LEBU effect. The results of 3 different setups were compared, with a smooth plate LEBU study completed using large eddy simulation with identical setups. Initially, the project was using ANSYS native meshing, like with the smooth plate, and with the smooth plate, this is fine on this bottom edge here, but for the LEBU, these in-between areas need to have a higher quality to simulate the large eddy breakup effect, and because these areas here were not of a high quality and weren't very refined, ANSYS native meshing would not be sufficient. It was at this stage the meshing software was switched to ICEM, which allowed much more control over the mesh. It allowed the geometry to be split up and each edge controlled, whilst always producing a quadrilateral mesh. After switching to ICEM meshing, convergence of residuals was no longer a problem, whereas before, with ANSYS meshing, the solution could not converge. Convergence is a measure of how closely the current iteration matches the previous iteration. It can be used to indicate whether a mesh is of sufficient quality in this case. Once the mesh problems had been resolved, the solutions could converge but were not matching those of the comparison study. After some testing, it was determined that the SST K omega model was not capable of simulating the LEBU effect. A study was completed to determine which models were capable of showing this effect, and finally the model was switched to the 5-equation Reynolds stress BSL model. It was shown this model could simulate the large eddy breakup effect without significantly increasing solve times. It also offered much better accuracy when compared to a 2-equation model, such as the SST K omega model. The final stage was to ensure the rough wall effect could be captured. For validation data, an LES study completed using a rod-roughened wall was used for comparison. Because of the limitations of using ANSYS and ICEM meshing, creating a wall consisting of more than 10 rods was not viable. The goal of the project was changed slightly to work around this problem. The investigation would now focus on how a rough wall and LEBU device together would affect flow of a fluid along a smooth wall following these geometries. With this in mind, the geometry for the rough wall consisted of 6 square rods. Each rod was placed 7 rod widths down from the next. No settings had to be changed for the section of the model creation, with the simulated rough wall matching the validation data. A brief study was completed to assess if Fluent's built-in roughness tool could be used in the place of the rods. This study showed that Fluent's tool could not accurately represent the rod-roughened wall and so could not be used. With this step completed, the actual testing with a rough wall and LEBU device could begin. The testing has mainly been looking at the skin friction over the wall when LEBU devices are placed in various positions above the rough section of wall. The boundary layers were also analysed to get an idea of what was happening after the rough wall and LEBU interaction. Actual testing was broken up into several cases, 1 through 5, each with one variable change to see its effect on plate drag. The final results of each of these cases were the reduction of drag and percentage net drag reduction. Case 1 and 2 used the same rough rod configuration combined with the LEBU device used in the second stage of validation. The variable change was where the LEBU device was placed above the rods, with case 1 having 1 LEBU device and case 2 having 2 LEBU devices. Because these cases did not produce a net drag reduction, the experimental setup was changed so that the LEBU device interacted with the rods more directly. Cases 3 through 5 had a LEBU device positioned directly above 2 of the rods. Case 3 placed 1 LEBU device above the first 2 rods, then the device height was varied slightly. Case 4 did the same, but with 2 LEBU devices, 1 placed above rods 1 and 2, 1 placed above rods 3 and 4. Finally, Case 5 placed the LEBU device at the most effective height determined in Case 3 and 4, then varied which rods it was placed above. Net drag reductions were observed for cases 3 through 5, with the largest reduction being in Case 5 when the LEBU device was placed above rods 4 or 5. It should be mentioned that drag reduction could be due to the scale of the experiment or because Rand's model was used, but these results are still promising and encourage further research into the area. These results prove the project to be a worthwhile endeavour for the area of fluid mechanics, and the project has been a success. Thank you for watching this video outlining my FYP.